So thank you, Livia, for the introduction. Thank you also for the invitation. It is a pleasure to be virtually in Nottingham. And so the title of my talk, as you can see, is Non-Archimedean Approach to Mirror Symmetry and to Degeneration of Varieties. So my goal would be really like to explain what do we mean here by a non-Archimedean approach to the study of mirror symmetry, and then to present a couple of results that follows from this approach. So I think that you all already heard about mirror symmetry, and you also probably already noticed that there are various approaches to the study of mirror symmetry. So in general, this is a phenomenon of duality between Calabi-Yaus, but there are various points of view we can tackle this phenomenon. And so today I will focus on a more geometric approach to mirror symmetry that it was inspired by a conjecture called the S weight Z conjecture. So I will state sort of original statement of the conjecture, but first let me fix the setting we will be working with. So we will consider families of complex Calabi-Yau varieties. So each fiber will be a Calabi-Yau of dimension n, and this is a family over what I denoted delta star, that is puncture disk in the complex plane. So here by Calabi-Yau, we mean a variety with a nowhere vanishing holomorphic n form, or equivalently a variety with trivial canonical line bundle. If you want to keep two main examples in mind during the talk, you can think of a K3 surface that is defined by the vanishing of a homogeneous polynomial of degree 4 in P3, or a quintic threefold that is, for instance, defined by a vanishing of a homogeneous polynomial of degree 5 in P4. So these are examples of Calabi-Yau varieties. But we will assume that we are working with a particular kind of families, and these are what they are called the maximally degenerate family. So here maximally degenerate means two conditions. So the first one is that we assume the family to be meromorphic at 0, meaning that we can extend the family over 0, and this extension that I will call curly X, that is now defined on the disk, not just the puncture disk, we assume that it's a smooth variety, and that the fiber that we're adding over 0 is strict normal crossing. So strict normal crossing means that it can be, it's not supposed to be irreducible, so it can have various components, but these components meet transversally. So this is what strict normal crossing means. And this condition of meromorphicity at 0, it can usually be achieved, applying result about resolution of singularity. So it's not a too strong a condition. What it really characterizes a family to be maximally degenerate is the second condition. That you can, roughly speaking, you can think that we want our family to be as degenerate as possible. So we want that when we get to the 0 fiber, it breaks into as many pieces as possible. And the way to say it more formally is that I say that we have various components in the spatial fiber. When the family is maximally degenerate, it means that there are a maximum number of components that intersect. So there is n+1 components that have a non-empty intersection. And this is the maximum possible. Otherwise, we cannot have more than n+1, otherwise we break the condition of being strict normal crossing. But we're really saying, okay, we break really into as many species as possible. So here, if you want an example of something that is maximally degenerate, that is almost maximally degenerate, I will say why it's almost. You can think of this family. So this family, you take F4, a homogeneous polynomial of degree 4, you can take it generic, and you consider T times this polynomial plus x0, x1, x2, and x3. And this is in P3 times our disk, basically. And so here you see that when T is equal to 0, then we have the vanishing of x0, x1, x2, and x3. So this gives us 4 irreducible components, and every 3 of them intersect. And this gives rise to these 4 green points. So the condition of being as degenerate as possible is achieved because we have n+1 components. And here n is 2 because for each, I mean, if we fix a fiber, then this is just a K3 surface. So where the fiber have Calabi-Yau dimension 2, and we have in the special fiber 3 components that intersect transversally. So the reason why it's not, strictly speaking, a maximally degenerate family is that this family is not smooth. Because in the special fiber, so in the fiber over 0, there will be 24 singularities that lies in the intersection of 2 of these components. So if you really want to get a family that will fit our setting, then we need to resolve this 24 singularity. But and this can be done easily, and you will still get such a family. Okay, so this was the setting. I will state the conjecture. So this is called SYZ conjecture from Strominger, Yau, and Zalov. And you really say, so I mean, the main content is that if we take a general fiber xt here, then the conjecture say that a general fiber xt should emit a fibration, so a map from xt to a base B. And now we will see what are the conditions on the base B and on the fiber. So on the base B, we ask it to be a topological manifold. And about the fiber, we ask that the fiber are what are called special Lagrangian real tori of dimension n. And this maybe is not achieved everywhere, so not for all the fibers, but at least away from a locus of codimension 2 in the fiber. So if you want to picture this, this conjecture, then this is the picture you can keep in mind. So we're saying that for a general T, there is such vibration that I denoted pi, such that almost all the fiber will be tori of dimension n, but then there could be some locus, this is the locus delta, where the fibers could have some singularity. For instance, here a picture like a pinched torus. So, I mean, if you, when I introduce mirror symmetry, I say that this is a phenomenon of duality between Calabi-Yaus. But if you read this conjecture, you just see one Calabi-Yau and like a strong existence property. I mean, the existence that given a Calabi-Yau close to the maximally degenerate limit, then there should exist such a fibration. So the idea that why this is considered as a geometric explanation for mirror symmetry is that from the SYZ fibration, from the existence of this special Lagrangian fibration, it should be possible to construct the mirror partner in such a way that for 2 varieties, for 2 Calabi-Yau varieties being mirror to each other, should really mean to have mirror fibration. So I mean to both admit a Lagrangian fibration over a common base, is such that if we avoid the singular fiber, then the toric fiber are dual to each other. So this is the reason why it can be seen as a geometric explanation for mirror symmetry, because you really try to answer the question, what does it mean for 2 varieties to be mirrored to each other in such a way that it means to admit dual toric fibrations. And the other reason why, I mean, it can be seen as like a starting point for the study of mirror symmetry is that once one SYZ fibration is given, then it should be possible to, I mean, this should be really the starting point for the construction of the mirror partner. So this is why, I mean, why it is considered in this way, and also why it inspired at least 2 major programs in mirror symmetry, one by Gross and Sieber, and the other one by Kontsevich and Soberman, because we really try to explain this phenomenon in a geometric flavor. So please interrupt if you have questions or if you would like to make remarks or add something. Anytime, just feel free to interrupt me. So this conjecture, unfortunately, is widely open. I mean, there have been recently some, I mean, nice new result by Yang Li, but I mean, the construction in general of an SYZ fibration is quite hard. And so today I want to, I mean, first say something, I mean, so today talks will be basically focused on the base B of this putative S with Z conjecture. So this will be the object we will try to study or approach by using non-Archimedean geometry. So before I move into more like a non-Archimedean world, let me say what kind of structure we know, we expect B to have. So B being the base of an S with Z fibration should inherit some structure from the fact that there exists this Lagrangian fibration. So I would like to point out what kind of structure B should have. Suppose that we have an S with Z fibration, then we already know that we expect B to be a topological manifold of dimension n. And we also have expectation of what should be the topology of this manifold. So in particular, if we take the three main building blocks for Calabi-Yau variety, then we know they are a street Calabi-Yau, an hyperkähler, or an abelian variety, then there are already results and evidences that B should be, in the first case, a sphere of dimension n. In the second case, for hyperkähler, the base should be projective space. And then for abelian variety, it is a torus of dimension n. So this is what we expect for B as a topological space. Then if we focus just on the locus B, where we have nice toric fiber, so if we remove the locus delta, then we also know that we expect B to have an integral affine structure. So what does it mean to have an integral affine structure? It means that we can cover B minus the discriminant locus delta with some open covers UI. So this is a manifold, real manifold. So we know that it is endowed with charts into Rn. And what we're really asking when we impose to be an integral affine structure is that these charts that goes to Rn are such that their transition functions are element in GLNZ. Okay, so we're just, normally there should be just continuous transformation and bijective transformation from Rn to Rn to be a topological manifold. But here we're really asking that our transition functions are linear in integral transformation. So this is what it means to be an integral affine structure. And as soon as we have an S with Z fibration, then from all the rich structure that we have on the fibers, we will get immediately that base B is endowed with an integral affine structure. So in some sense, this is what we will then expect when we try to construct B without having already the S with Z fibration. And then there is a third element that I just want to mention, but we will not really focus on this part, is that so we can think of B as a metric limit of the space xt, because we can endow the space xt with a metric such that in the limit, so our space xt has a lot of toric fiber, and we can endow it with a metric such that the volume of this toric fiber will collapse, such that in the end, the metric limit is B itself, because the fiber just collapsed. And from this, we can, since B will be endowed with a metric that is a metric limit from the metric of xt, we have some properties on the metric on B. And in particular, this is what is called a Monge-Ampère metric. So just, keep in mind this notion. It's possible that you will encounter again. So that's why I wanted to mention that this is also another piece of information we have on the structure of B. But the insight we will start with to study B is an insight by Kontsevich and Soiberman. So their observation, they probably also, was already mentioned by Loeg and Baffa, is that in this setting, when we have this family, we have two kinds of limit. One is the metric limit I just mentioned. So we can endow the xt with a metric such that the fiber will collapse. And so the metric limit will just be the base B. But we also have a geometric limit. So our family is degenerating towards, towards 0 to a fiber x naught. And so the insight of Kontsevich and Soiberman was that try to study this metric limit from a geometric perspective, and in particular to relate the two limits, the metric limit and the geometric limit. And this question led them to suggest that the base B should be related to the general fiber X0, sorry, to the special fiber X0, if we consider the dual complex. And they also went further. They also say that this dual complex should be embedded in a Berkovich space. So this last sentence, as I say, is probably something that you're not familiar with. And this will be what I will explain now. So I will explain what is a dual complex and what does it mean that we can see a dual complex embedded in a Berkovich space. And just keep in mind the motivation. So the reason why we will talk about the dual complex and this embedding is that because we expect the base B to be related to this dual complex, or even like to be, really like being isomorphic to this dual complex. So that's why we are interested in understanding these two notions, dual complex and this Berkovich or non-Archimedean space. Okay, so if there are no questions, then I'll move to explaining this part. Okay, so let's start with the notion of a dual complex. So, the notion of dual complex is more general. For us, it will be the dual complex of the special fiber. So, our setting will be that we have a family over delta star. We consider an SNC degeneration. Here it means that we are really, it's the same we explained before. So we're adding a fiber that is a strict normal crossing variety, and we're assuming the total space to be smooth. So it means that our X, curly X0 is an SNC variety. Whenever you have given an SNC variety, you can define a dual complex. And this is the definition. So let's suppose that we have Y, an SNC variety, that, as I said, in general is given by some irreducible component that I denoted here Yi. Then the dual complex is a cell complex. So I need to give you 0 cells, there will be points, then I need to give you edges, like 1 cells, and I need to tell you how they are patched together. So let's start with the 0 cells. For any reducible component Yi, we will associate a 0 cell Vi. So a point for any irreducible component. Then if two components intersect, I want to add a cell joining Vi and Vj. But it's also possible that these Yi and Yj they intersect in many reducible components. So I want to remember this. So I will add more than 1 cell joining Vi and Vj. So it means that for any reducible component of a non-empty intersection, we will have a 1 cell. And then this, you can just continue this process and say that for any reducible component of k plus 1 irreducible component of Y, you will add a k cell. So let me be very concrete and give you some example that will make the definition, I believe, much more clear. So suppose that we have just 2 components, Y1 and Y2, and they intersect in 2 points. Then we say that if we follow this construction, we will have 2 0 cells, V1 and V2. And then we were looking at the intersection between Y1 and Y2. These are 2 points. And so we will have 2 1 cell joining V1 and V2. Now let's look at a basic example in higher dimensions. So let's suppose that we have 3 hyperplanes meeting transversally. So these are 3 hyperplanes. So we'll have V1, V2, and V3. 2 of them intersect along a line. So we'll have 3 edges. And then we'll also have an intersection of 3 of them. So this is the point where Y1, Y2, and Y3 they intersect. So now we will add 2 cells that fits this triangle. So let's look at also the example I stated at the beginning. So this family of K3 surfaces. We've seen that the special fiber was given by these 4 hyperplanes in P3. And so we see that here we have 4 components. So these will be our 4 vertices. 2 components meet along a line. So this will be our edges. Then we have the 3 the three components meet together at a point, and so this will give us the phase. So we don't have four components that meet all in the same point. So this tetrahedron is just the boundary of the tetrahedron. It's not like a full tetrahedron. So we will see that, I mean, this dual complex is really homeomorphic to the sphere, to the two-dimensional sphere. Okay, so this is the notion of a dual complex in general, and we know that as soon as we assume our family to be to degenerate to a string normal crossing variety, then we have this topological object, okay, that is constructing, I mean, that is a cell complex. So the idea is that now this is a dual complex, we want to embed it in a bigger topological space that is called a Berkovich space. And I mean, I will try to give you motivation of why it's interesting to see this embedded inside a non-Archimedean space rather than just a cell complex, an abstract cell complex. Okay, so right now there will be like a slightly shift of setting. So in some sense, we need to work in a more algebraic setting. So we want to work not just with the whole family over a punctured disk, but we want to work with a generic fiber of our family. So we can just think that we are just shrinking around 0 and taking a generic fiber. So we're working with a variety that is defined over C double bracket T. So you can really think that your projective family was like algebraic over T, then over algebraic with respect to T, and so you can think of this as a variety over C double bracket T. Okay, so I mean, technically, algebraically, the reason why we want this is that now K has a natural valuation, and we need this our base field K to be endowed with a valuation in order to construct a Berkovich space. So this is like why we shift to this setting. Okay, but if you want to keep a geometric intuition, let's just think that now I still have my family, but I'm focusing on a generic fiber of the family. Okay, and associated to this, we can construct what is called a Berkovich space. So this is a topological space, and the points in this space are valuation. So most of the valuation that we are be interested in are valuation on the function field. So let me just remind you, what do we mean by valuation? So when I fix a field, in this case will be the function field of the variety X, a valuation is a map to R such that two condition holds. So it's such that when we consider element A, B, the valuation of their product is the sum of the valuation. And when we consider A plus B, the valuation of the sum is at least the minimum between the two valuations. So to be really concrete, so let's take our base field C double bracket T. For instance, a valuation we can consider is the order of vanishing along T. Because if you take any series, so any element in C double bracket T is a series, and we know that there exists a minimum n0 such that a n0 is different from 0. So I mean the first non-zero coefficient in our series. Then the order of vanishing with respect to T is really n0. So it's the first power of T that appears in our series. You can check easily that this is a valuation in the sense that it satisfies the two above condition. So when we talk about a Berkovich space, we're saying that we want to enrich our space X by looking at all the possible valuations that are defined on points. And in particular, we will be mainly interested in this subset of all the valuations that are defined on the function field of our variety. But don't worry about what is a Berkovich space. I will give you a picture and example that will make it, they will give you like a better intuition of how this space look like. Okay, but so remember, we want to say we were starting from an SNC degeneration. So a degeneration of our family such that the special fiber is an SNC varieties. We say that we can attach a dual complex, And then my claim is that this dual complex can be embedded in a Berkovich space. So I just told you that the Berkovich space is a space of valuations. So what I need to explain is like how to give a valuative interpretation to the dual complex. Means that to each point of the dual complex, I want to associate a valuation such that the dual complex will be embedded in the Berkovich space. So, and this can be done, it can be done canonically. So I give you the idea for the vertices, for instance. So suppose that I take a vertex V1. So a vertex in the dual complex comes from a component D1 in the special fiber, okay? So locally, my component D1 has a defining equation, F1 equals 0. Now I can automatically attach a valuation by taking any other element in the function field of the variety, considering what is the power, the maximum power of F1 that divides F. So I can write my F as F1A times H, where H is not divisible by F1. And then the order of vanishing along D1 of F will be just A. So this is really like copying, sort of inspired by the definition of order of vanishing along T, but now it's order of vanishing along the divisor D1. So this gives you an idea of how we can see the points, the zero cell V1 as a valuation. So we can see it embedded as an order of vanishing along D1 inside the Berkovich space. And then, you can wonder, what about the other? This holds for the zero cells. What about points that are in higher dimensional cells? Then the way you can think of it is like we will construct valuation that are sort of interpolation between order of vanishing along divisors, okay? In such a way that the whole dual complex will be embedded in the in the Berkovich space. And we will, so the image, once the dual complex is embedded, I can call the embedded image a skeleton. And as you see by the notation, this skeleton really depends on my degeneration. So even if X, the generic fiber, is fixed, so I'm not changing the family away from 0, it's really, this dual complex really depends on the special fibers, so really depends on the degeneration that we are considering. And this is the reason why we call it SK and then curly X. So now we have an embedding of the dual complex inside the Berkovich space, and we call the image a skeleton. But then in the non-Archimedean world, we also have a way to retract the whole Berkovich space onto the skeleton. And this is even a strong deformation retraction. So strong deformation retraction implies that the whole Berkovich space and the dual complex, the skeleton, have the same homotopy type. And so already this is, this makes this dual complex particularly interesting because it tells us that if we can study the topology of these dual complexes, then we basically know up to homotopy all the properties of the Berkovich space itself. Okay, but so I will now say more and also give you a way to construct a full Berkovich space, of course, in dimension 1, to give you like a better intuition. So what we did so far is the following. We fix a variety over a puncture disk, or algebraically we can think of over K equals C double bracket T. We say that we can construct a topological space that is a space of valuation. Inside this topological space, we have all the dual complexes for all the degeneration, for all the SNC degeneration. So for instance, if here my degeneration is such that in the special fiber I have 3 components that meet transversally, it means that inside the Berkovich space, it sits this nice triangle, and this is like a skeleton. But of course, I can change my degeneration. I know that I cannot touch the generic part, but I can always like make some transformation that only affect the central fiber. For instance, suppose that by, for instance, some blow-ups, we had a new component in the special fiber. So we get a new model curly x prime, where the special fiber curly x naught prime is different, as one component more. Then we will see that also the skeleton changes, right? Because we'll have a new vertex, a new intersection, and new faces. So you can imagine that we take more and more models, so we can construct more and more models by doing like birational transformation that only affect the special fiber. And what Berkovich proved is that in the end, when we take the limit of all the skeleton, we are getting the whole Berkovich space. So I mean, if you really want to have like a concrete way to think of a Berkovich space, I think this is the best one, because you need to think of a Berkovich space as having some nice cell complex inside that comes from the geometry of the variety. You degenerate the variety, you have the special fiber, so you have the dual complex, and this sits inside the Berkovich space. And this is just, I mean, one simplicial that it sits inside. But then if you let the degeneration vary, then you can basically approximate all the points in your Berkovich space. Okay, so let's see this approximation in a one-dimensional case. So suppose that we start with an elliptic curve over K. And suppose that we have an SNC degeneration that is also minimal, such that the special fiber is a loop of rational curves. So a loop of rational curves, here I just draw 5 of them. So it means that this is how the special fiber looks like. So if we construct the dual complex, then this will be given by, so here there are 5 components, so 5 vertices. And then they all intersect along a point, so I will add these 5 edges. So now this dual complex is, we say that it sits inside the Berkovich identification, so we know that this S1 really sits inside the Berkovich identification of our elliptic curve. So now we can think of how we can get other degeneration of the same elliptic curve. So there are basically two operations that we can look. So we could blow up a point that is a smoothed point, or we could blow up a point that is a node in our special fiber. So this, I mean, all the birational transformation can just be obtained by composing these two kinds of blowups. Okay, so if I blow up a point that is a smoothed point here, then we are really adding a new component. And at the level of the dual complex, it means that we're adding a new vertex given by the component, and also a new edge, because we also have this new intersection with the new exceptional component. So it means that in our Berkovich space, we are adding a new edge sticking out from the S1. Instead, if we blow up a node, then we will have our old 5 components and a new component, a green one, that has now 2 points of intersection with the old components. And this basically corresponds to subdividing the edge that was joining the 2 components that define the intersection of the green point. So it means that I can always take this S1 and basically subdivide by considering blowups of nodes. So you can imagine that these 2 operations that I've just done can be, can be performed many times. So I can at the same time add new edges by blowing up smooth points or subdividing my edges. And I can keep doing this, so we can subdivide and blow ups. So in the end, if we keep doing, so if we do this limit, the picture that we'll get will be a sort of an infinite tree that has inside, that contains an S1, okay? Just by, keeping branching our points and subdividing and adding new edges. But what is important is that inside there is this S1 that was the skeleton of the minimal model we started with. And what is also important that we know that we can retract all the Berkovich space onto this S1. So here you really see the retraction. So the retraction will basically collapse all these branches back to the S1. So back to the points where the branch is attached to the S1. So you see like visually how the retraction works, and you also see why they have the same homotopy type. Because I mean, adding these new edges does not affect the homotopy type. We can always retract them back. So in the end, we get the same homotopy type for the Berkovich space of E and the totals and the skeleton S1. So this is an example that I think it's quite rich, and it's also, I mean, give you a feeling of what are the objects that we are working with. So when we work in one for Berkovich space of variety of dimension 1, then we usually work with this infinite tree. It's much more difficult to visualize a Berkovich space attached to higher dimensional variety. And the best way to really work with and visualize is think of this as the limit of all the skeleton. So I mean, this is the way that I geometrically think of. So I know that it's like simplices that gets bigger and bigger. Okay. So, but this retraction that I mentioned here from the elliptic curve to the S1, it was, I mean, it's a sort of inspirational example also for the program that Kontsevich and Soberman proposed. So they proposed what they called the non-Archimedean approach to mirror symmetry. And the idea that they had is that really this kind of retraction that here is defined in the one-dimensional case should resemble a non-Archimedean analog of an SYZ fibration. So the SYZ fibration that we're looking for in the classical complex world should have an analog in the non-Archimedean world. So when we pass from X to the Berkovich space, and this kind of retraction should really mimic the SYZ fibration. So I mean, this is why I mentioned, and I wanted to show you this retraction, and you will see, like in the sequel, that this retraction will indeed be studied, and I mean, you will see really like how their inside really inspired result that goes in this direction. So in like thinking of this Berkovich retraction as analog of an SYZ fibration. Okay, but you see immediately that there is a problem. So let's just sum up what we did so far. So we started with an SYZ conjecture. We said that we wanted to focus on the base B, and then we wanted to see the base B as a dual complex. So this is done. Then we say that, okay, this dual complex is now a skeleton, so it's embedded in a Berkovich space. And also it comes equipped with a retraction, this Berkovich retraction. So the problem now is that here it seems that our base B really depends on the degeneration, right? Because if it's a dual complex, then I mean the skeleton really depends on the spatial fiber. But while in B, it seems that I mean it should not depend. I mean B should only depend on the generic fiber. It does not depend on how we really feel the fiber over zero. So it means that among all these skeletons that we're looking at, all these skeletons that define that, for instance, that sits inside the Berkovich space, we should be able to find one that is canonical, one that is minimal, so one that could really play the role of our base B. So here in the one-dimensional case, I cheated because we know that we have minimal SNC degeneration. So this is a natural candidate to play the role of a minimal canonical base for our retraction. But in higher dimension, there is not such a notion. I mean, this notion will not give you like a unique dual complex. So this was a problem that already Kontsevich and Soberman tried to tackle, and it led them to the notion of an essential skeleton. So among all the skeletons, we need to construct a good notion of skeleton such that will allow us to pick one particular skeleton among all the others. Okay, and also, I mean, we don't just want to be able to construct, we also wanted to have this retraction. So this is the notion of an essential skeleton that I will now try to present. So here we still have our variety, we have our Berkovich space, and we know that for any SNC degeneration, we have a skeleton that sits inside the Berkovich space. So the idea of Kontsevich and Soberman is that inside any skeleton for an SNC degeneration, there should be an essential skeleton that only depends on X, so that does not depend on the choice of a model. Maybe to construct the essential skeleton, you will use a model, but in the end, this is independent on the choice of the model. So let me say that, so this is, the first notion of an essential skeleton is contained in the work of Kontsevich and Soberman. And then later, there have been two approaches to define this essential skeleton. One is to define the essential skeleton really by using notion from the Berkovich world, so like a non-Archimedean definition of the essential skeleton. But there is also a second approach that is by using some birational construction, like to characterize these skeletons in terms of the birational geometry of the model you need to take in order to construct the essential skeleton. So I will now say more about these two approaches. First of all, let me say, the major work in the development of the notion of an essential skeleton is due to Mustat and Ikese and Xu. So they basically develop and generalize the idea they were contained in the Kontsevich-Soberman work, and they were able to define this essential skeleton. And first, they proved that this is a birational invariant of X. So it only depends on X, but not always. It's really a birational invariant. So if X and X prime are birational, then they will have the same essential skeleton. And it does not depend on the model, on the degeneration we pick. Then the second question is, the second properties that they proved is that, so this essential skeleton, if we only use the non-Archimedean definition, it will be, the definition will look like inside a skeleton, select some of the faces according to a certain condition. But it will not tell us if this new subcomplex that we are looking at, it still comes, it has a geometric origin, if it comes from a model. So what Ikese and Xu prove is that indeed the essential skeleton is still a dual complex. So it's still like a dual complex attached to a special fiber. But now we cannot work with SNC degeneration. We need to allow more singularities in order to have a distinguished dual complex, and the singularity we can work with are what they're called the minimal DLT singularities.
Excuse
so
me? You have a question?
Yeah.
For the second definition, if you want to consider the minimum DLT degeneration, does it relate to the result of the existence of the minimum model program, like DLT minimum model?
Sorry, can you repeat again? So you say if I take the second definition?
Yeah, you want to consider the minimal DLT degeneration, right? But what I'm just wondering is is this definition relying on the result of the existence of the minimal model program, like from the minimal model program?
So you mean if this definition relies on the minimal model program, or is it this the question?
Yeah, because you want to consider minimal DLT, right?
So I think that you can define this without reference to the minimal model program, because you can just see the essential skeleton as a subcomplex in an SNC degeneration, in the skeleton of an SNC degeneration, and take the faces that will be minimal with respect to a certain condition. So this allows you to define the essential skeleton without using any MMP techniques. But the point is that in order to prove this equality, then you use more you rely more on the result of the MMP, because you really want to see this essential skeleton comes from the dual complex of a minimal DLT degeneration. And there, I mean, at least, I mean, for instance, you need to assume that there exists one. So, I mean, here there is more like birational techniques that will play a role. But if you just want the definition, then you can take this Berkovich approach and you will define it. But for instance, according to this definition that is more general, you can also have that the essential skeleton in some cases is empty.
Okay.
But of course, this would not be like the interesting notion. I mean, I think that there is a sort of big overlap by, I mean, you will focus on the cases where it's interesting to study the essential skeleton. And in those cases, you want also to play with, I mean, birational results and birational techniques. Yeah.
Okay. Yeah. Thank you.
Yeah, you're welcome. Okay. And then, so the fact that the essential skeleton is given by the dual complex of a minimal DLT degeneration is, first of all, interesting in itself, because we really say that these two approaches are giving us the same object, but it's particularly important to say, I mean, to conclude that we still have a retraction. I mean, if we didn't have this equality, the second one, then we would not be able at the moment to also say that the Berkovich space that we knew could retract to skeletons now also retract onto the essential skeleton. And here I mentioned that this retraction is non-canonical in the sense that even if the base does not depend on the model, on the minimal model we are working with, the retraction does depend on the model. So it could be that we have many different retractions onto the same essential skeleton given according to the particular minimal DLT model that we choose. Okay. Okay, so here we see that, okay, we can, so I mean, this is the one that I just mentioned, this retraction is a case where we have this equality and we are really focusing on the fact that we know that the essential skeleton is the dual complex of a minimal DLT degeneration. So by knowing the birational characterization, we get something about the, I mean, we gain a result on this retraction in the Berkovich world. But we could also play the game the other way around. So we like, suppose that we know the essential skeleton, does this say something about the geometry of minimal DLT degeneration? Or maybe does this allow us to describe the dual complex of a minimal DLT degeneration without constructing the minimal DLT degeneration? So this is the idea that sits behind a result that I proved in collaboration with Morgan Brown. So here we took some families of hyperkähler. So we took X to be birational to the Hilbert scheme of endpoints on a K3 surface. And we also look at the family when we look at this K and A, these are the generalized Kummer varieties. These are both families of hyperkähler. And what we prove is that if we are in the maximally degenerate case, then the essential skeleton is a projective space. So first of all, so we already encountered this projective space, and we encountered this at the beginning of my talk when we mentioned the expectation on the base B. So if now we expect the base B to be the essential skeleton, and in the classical setting, we expected B to be a projective space. Here, we're really proving that the essential skeleton is a projective space. So this, I mean, this is an evidence that the base B and the essential skeleton, I mean, it's reasonable to expect that they are relating. And this is just another evidence. I mean, they were already. But what is also interesting in this result is that if we try to prove to study the dual complex of a minimal DLT degeneration of an Hilbert scheme, then what is difficult is really to construct the minimal DLT degeneration. I mean, by MMP result, you know that it exists, but I mean, this result is general in a way that you cannot really describe the dual complex. You will not be able to conclude that this is really a CPN. But if we study this dual complex as an essential skeleton, then it becomes much more easier to conclude that this is a CPN. So, I mean, this is just to say that when we look at this equality, we can really play from both sides. We can do some Berkovich construction and like study the essential skeleton, it gets information about dual complex of degeneration, or the other way around. We can play with minimal DLT degeneration and conclude that, for instance, we have a retraction. So just to tell you what was, I mean, I think that I want to add this small remark that if we use the rational geometry of the degeneration of hyperkähler, at the moment, the best result that you get about this dual complex is it was proved by Collard, Laza, Sakya, and Voisin. You can prove that the dual complex is, as the rational homology of a projective space. So this result is more general because it works for any 2n-dimensional hyperkähler that is maximally degenerate. But it's in the case of Hilbert scheme and generalized Kummer variety, they were able to take this characterization of the Q homology and really turn it into a characterization of the homomorphism type of the essential skeleton. So in some sense, it's an improvement, but just for these two families of hyperkähler. Okay, so this was, so the reason why we introduced the essential skeleton is because we say in the S with Z vibration conjecture, we know that the base only depend on the special fiber, on the generic fiber. So if we want to have an analog in the non-Archimedean world, then we need to find a way, a good candidate for a minimal and canonical skeleton that could play the role of the base of our retraction. So Kontsevich and Sommermann came out, proposed this essential skeleton, and then the work by Mustat and Nikhazy Su proved that indeed there is a retraction. But they went, they even made a step further. So still in the same setting, but just now we focus again on the Calabi-Yau case. So we've seen that we have this Berkovich space, we have all the skeletons, and then inside we really have the essential skeleton. So what Nikhazy, Su, and Yu proved is that if we fix a good minimal DLT model, so that we have the retraction onto the essential skeleton, then this retraction that we know exists from the work of Berkovich is in particular an affine torus vibration away from a locus of codimension 2. So from the name affine torus vibration, one should really think that this is an analog of Lagrangian torus vibration. But let me tell you what we mean here by affine torus vibration. So here we have our retraction that we know it exists. It's not canonical, but it exists. It's enough to have a minimal good DLT model to have such retraction. And then what the result by Nikhazy, Su, and Yu are saying is that at least, locally, this map is isomorphic to the map from, we take a torus of dimension n, we took its analytification, and there is a canonical way to retract the whole Berkovich space associated to a torus to Rn. And this is called a tropicalization map. Basically, it takes a valuation. Remember that the Berkovich space is always a space of valuation. So an element point is V, it's a valuation. And if we fix coordinate for our torus, Z1, Zn, then it will just associate V to the valuation of the coordinates. And this is an element in Rn. So what they prove is that this retraction is locally isomorphic to this tropicalization. But this tropicalization really say that like the fibers are, this space is the analytification of a torus. So we're really saying that this map is built up from analytification of tori. So this is why it's called an affine torus vibration. And again, this local isomorphism will hold, but everywhere except away from a locus of codimension. Except a locus of codimension 2. So this is what they consider to be a non-Archimedean analog of the S with Z vibration. I mean, from the property that this retraction turns out to have. And now, so the game we want to play is really like saying, okay, we understood that this is expected to be related to the base of the S with Z fibration, but now in the non-Archimedean world, we are really always able to construct this map. While in the classical world, constructing an S with Z fibration is much more harder. So, I mean, the idea that it sits, that is at the base of the Kontsevich-Soberman project is, instead of solving the S with Z conjecture, let's just move to the non-Archimedean world, where we have a non-Archimedean S with Z. And then from here, let's try to construct the mirror. And I mean, there is a whole program that is still like in progress, okay? But really, I mean, the linking, the bridge between the two worlds is really this base, because we expect that the essential skeleton is the base B. So at the same time, there is a topological space that is both the base of the classical S with Z, but also of the non-Archimedean S with Z. And so if you remember, I said that this base B comes with an integral affine structure, a metric. So we can also wonder, what about the essential skeleton? Does it also come with an integral affine structure? Does it also have a metric? And if it does, can we compare it to what we get for the base B? So from the fact that this map is an affine torus vibration, we get an integral affine structure. And so what I'm investigating at the moment is really to compare the two integral affine structure. So for instance, if we consider just the K3 surface case or the quintic threefold case, then we know that using S with Z, our essential skeleton, we already know that we will get a sphere, okay? But using the non-Archimedean S with Z fibration, our essential skeleton will have an integral affine structure. And what I'm proving with collaboration with Léonard Pille-Schneider is that we can construct, by using the non-Archimedean S with Z fibration, an integral affine structure that is exactly the same you will get on the base B. So this is a further evidence that really the essential skeleton and B, they do not only have the same topology, but it's also possible to construct with different tools, in my case, the non-Archimedean tools, the same integral affine structure. Okay, so I mean, I think that this is probably this is probably the picture, the diagram you should keep in mind from this talk. So we have like this classical world where we're looking for an S with Z fibration, but this is still a conjecture. We have insights from Kontsevich and Soberman that the base should be related to a dual complex. We have all the work by Nikese, Mustata, Xu, that really, to characterize a minimal dual complex, we need to look at minimal DLT degeneration, such that this will define an essential skeleton. And now in the non-Archimedean world, we always have this S with Z fibration. So I mentioned that there are works in progress that really exploit this non-Archimedean approach. I think that, two main people that I could mention, one is Tony Yu, that's really trying to develop all the necessary foundation on the non-Archimedean sides to be able to construct, to basically run the construction of the mirror in the non-Archimedean world and then try to go back using some Gaga result. But it was also really interesting, the recent work by Yang Li, where, it works in analysis and he wants to really construct the S with Z fibration. But what he proved is that it's like by resolving, by studying this non-Archimedean S with Z fibration, that he can, he has a conjecture in the non-Archimedean world that will imply the existence of an S with Z fibration in a large portion of the variety XT. So this is really showing that the two approaches is not just that one mimic the other, it's not just an analog, but they're really like, one is really the asymptotic picture of the other one. So in order to construct even the S with Z conjecture, it's possible that we need to go through some non-Archimedean results. At least this is what Yang Li is recent result proved to be too old. Yeah. So I think that I will stop here. I thank you all for your attention, and yeah, maybe I will stop and share so that I can see if you have questions.